Live.
The fog over the North Sea was thin, high, and lit silver by the morning sun. At 7,000 feet, Graf Zeppelin II drifted silently along the English coast, its engines throttled low, its massive shadow sliding ghost-like over patchy farmland below. Inside the gondola, Oberfunker Helmut Stein hunched over a panel of dials and wires. The headphones were warm against his ears, but the signal was cold, strange. A pulse, then another, 25 hertz, precise, regular. Es ist weiter da, he muttered, tightening the dial. There's a buzz. Where? Came the reply. He pointed silently. East, toward the flat marshy coastline near Dover. Repeating every 4 seconds. It's not broadcasting, it's probing. Above them, on the horizon, a row of steel towers pierce the sky like crude scaffolding for a ruined cathedral. 4 tall ones, flanked by smaller ones. Ugly, functional, British. The towers didn't match any known transmission site. Commander Hugo Eckner, pacing behind the observers, glanced at the schematic sketches coming off the desk. Those aren't power pylons, Stein said under his breath, but the logs would later say otherwise. Ooh, that sounds real mysterious. Don't you agree?
Absolutely.
Absolutely.
Hey,
Who is this? All right, I'm bringing somebody else on.
what are we doing here?
This guy, who is he?
Hey, Shen.
Hey, good to see you.
Hey, what up? I clicked on a link that had something to do about the history of radar, and then you're talking about a Zeppelin, the Hindenburg.
Yes.
The Hindenburg. Which?
It's not the Hindenburg. No, not the Hindenburg. No, we're gonna get to that today, actually. The Graf Zeppelin that was flying over Britain in 1939. But really, you ask a good question. Like, what exactly is this, right? So this is what's formerly known as SG-2 on space. New name, still TBD for now, but whatever it happens to be, it's episode 229. And we are, last few times we talked about mysteries. This time we are talking about something that actually people know quite a lot about, radar. Specifically the invention of radar in terms of the science behind it, how the theory was turned into technology, what the British did, their major breakthrough. Obviously the Zeppelin incident, which was, prefacing like what I just said, the story, initially starting this episode. And then how radar was obviously used during wars, notably World War II.
Important.
And then we will talk about exactly how much of our modern world has been shaped by its invention and what would it look like if it never existed. So, does that sound like a good plan?
Sounds good to me.
All right, Leonard, you're the carrier of this knowledge here, so I'm going to lean on you to expound on a lot of questions.
So, let's see. Where do we begin? I would say let's begin at the beginning. I guess we can go back all the way to the 19th century to talk about how radar got started. So the story it sort of began in quiet labs where invisible waves. The
Invisible waves, yes.
The radio waves that we know about were just beginning to be understood. So we did a show on James Clerk Maxwell, I think, a couple of years ago.
We did.
I think we did. His equations in the 1860s, he published a paper in 1861 or 62 that essentially have the modern Maxwell equations that predict that light, magnetism, and electricity are all part of a single spectrum of things. And in particular, his equations showed that this thing called electromagnetic waves or the had there was a wave solution to these equations, but he never saw these waves exactly. But
Are you talking about Maxwell's equations?
talking about Maxwell's equations, so sometimes
Okay, let's see if we can pull
yeah,
this up.
sometimes you'll see nerds with
Boom.
t-shirts.
Yeah, I thought about getting one of these nerd T-shirts of Maxwell equations.
Yeah, it's sort of passé for me. I mean, I'm too cool.
I get it. It's like, okay, done deal. You already know all this. But for people who don't know these equations, why are they important and what do they signify?
These are modern wave equations that that explain the phenomenon of the electric field and the magnetic field and unify them together. And they have wave solutions to them, and those waves are radio waves. He also postulated that it's sort of scale invariant. In other words, the wavelength can be any. The equations for electricity and magnetism propagating through space can exhibit any wavelength, any frequency or any wavelength, and even up until today, that is an issue of scientific inquiry. So later on, about 20 years later, lots of people in Europe were playing with these, doing experimental work and doing research because they knew about telegraphy, using telegraph to communicate, and in particular, one of the big problems was in transatlantic cables. There was some certain kinds of distortions that were observed, and that sort of thing. So there's all kinds of physics, the physics of electrical insulation. How does electric insulation change the propagation of waves? And so enter Heinrich Hertz. So Hertz, and we actually
like Hertz, the units for frequency, that's named after him.
The units for frequency are named for Hertz. So he's got a unit named after him.
I mean, that must mean you've done something important.
I don't have a unit named after me.
I mean, yours would be what, the Kramer?
Yeah, I don't know. That would be a great achievement. So he built the first system to generate and detect radio waves, and he also observed that they reflected and refracted just like light. Okay, except at much longer wavelength.
Huh.
So, and so actually he didn't really realize that there was very much use for radio. I think at some point he's quoted as saying, if anybody asked him about it, he says, no, it's just an experiment. He's just studying the phenomenon. But radio, real radio started to come into popular interest. There was an inventor named, and I never heard of this before I did the research for the show here. His name is Christian Hulsmeyer. And in 1904...
Hofmeyer?
Hulsmeyer.
That's a pretty...
I never heard of him.
There doesn't seem to be a picture of him on Wikipedia, but I'm sure. Okay, so he invented something called, he called it the telemobeloscope.
Yeah. So
great name.
This was a device. It had like a little horn antenna, like a parabolic antenna, and then he used the way they created radio waves is they just used an induction coil to raise the voltage on a capacitor, and then they would arc. So they would make an arcing. Maybe we've seen it on television or some movies where you'll see the telegraph signal, and it will trigger an arc, and the arc gives off a lot of broad spectrum radio waves. And so he ran it through a little parabolic horn, and then he had some kind of detector, and the detector the way the detector worked was pretty interesting too.
This thing. By the way,
this
is it. That's Which one is the detector and which one is the horn thing?
Well, I think in this case, he's just got those two dipole. He's got that dipole. This is not the case. The patent. I took the information that I had from the patent that I saw published, Um,
Oh, okay.
but for this example, that's in a museum somewhere in Germany.
Mm-hmm.
There's two dipole antennas that are sticking out at the top.
Yeah, I see that.
So they would create an arc, and the arc would create a wide spectrum of electromagnetic radiation. And in fact, it's illegal today. It's like, why is it illegal? You know,
What is illegal to make this?
to make a arc. I don't exactly I don't exactly know what it's called, but it's if you use an arc, an electrical spark to create a broad spectrum pulse, because to communicate that way, because it contaminates the environment with broad spectrum radiate. I'll use the word radiation, and I don't mean anything that's like really dangerous. I just mean
Right.
electromagnetic radiation.
Right. So to
Right.
make a broad spectrum pulse with this, the
Yeah.
arc, is illegal these days because it interferes with the
It,
existing radio signals.
it creates interference. So
I
I'm
see.
pretty sure I could make this device. I'm pretty sure I could, I could put something together. But so the other thing is the detector is pretty interesting. The way radio waves were detected was they used they used I want to say iron powder, metal powder, and the powder was packed into a cylinder, like a glass cylinder, with some conducting. You put a potential across the powder, and then
Mm-hmm.
it had this property that when a weak radio signal would pass through it, it would tend to polarize it or bring it together, bring it all into alignment, and it would temporarily conduct electricity. And then you had to tap it, so that it had some kind of vibrating device on it to keep it apart. But then when the weak signal that's reflected. So the idea with Holzmeier's device was it would send out this broad spectrum of radiation, electromagnetic radiation, and then if there's a ship nearby, like in the fog, that was
Mm-hmm.
really what the patent was all about. In the fog, then the ship would reflect it back to the receiver, and the receiver seems really ludicrous the way it works. It's like it's powdered metal, powdered iron, and then it would conduct electricity briefly when the received signal, the reflected signal, came back to it, and then you would know that there was something there. It didn't have any directional capability. It just could say if you started hearing this signal through the detector, it would it would
But
tell you that a short was.
it was a first attempt. I mean, that's what's important.
And yeah, he demonstrated this, I think, for the German government, and I think nobody was really that interested in it, and it kind of like fell
It's
by the wayside.
presented at on May 17th, 1904. I'm reading this out loud. He demonstrated the telemobiloscope in the courtyard of the Dom Hotel in Cologne. Using a metal gate, Holzmeier proved his device could detect objects even when not directly visible, showcasing the practical application of his invention, earning him significant acclaim. And then he presented at the Maritime Safety Conference in Scheveningen, Netherlands. So,
So anyway,
but
I mean, I'm trying to imagine myself like
yeah,
back then in my steampunk world, um, that you can't see through the fog, okay? And
mm-hmm,
in all of human history, people would not be able to see through a fog. There's a ship out there, and you have a device that either makes a little buzzing sound or maybe even lights up a little light bulb for you, and it's saying there's a ship in the fog. And I'm thinking, wow, that would be, just if I can just transport myself back in time. I just think that's really cool. You know, forgetting everything that I know about modern world and so forth. So this was a very exciting time, to be doing this kind of experimental work. And so in the 1920s, so during the next few years, radio itself was used for the first time in 1904 by the Japanese in the war with Russia. the Russo-Japanese War that the Russians lost badly to Japan.
They lost, you're saying, partly because of the usage of
Yes,
radio?
yes. The Japanese were able to exploit radio communication to coordinate their attacks or in defense, and they used similar kinds of technologies that I just described. They didn't have radar at the time, but they weren't using radar, but they were using radio. Morse code. They didn't have amplifiers, so they had to. So it had those kind of limitations to it. But I think that's pretty interesting that radio was used for the first time in a military case by Japan against Russia. Russia also had some kinds of radio also, but they didn't use it effectively. I think because of organizational problems or
I see.
Just being Russian, maybe, I don't know. So,
Oh my
anyway,
gosh.
so during by the 19 teens, radio itself as a form of communication was pretty well developed. Even the Titanic, which sank in 1912, had a radio transmitter famous for being able to make contact with a nearby ship, and then the ship had their radio set turned off because, I don't know, they had it turned off.
So you're saying the Titanic had radio, but it could not detect the iceberg?
They had radio. No, not to detect the to send out a request for help. Okay, they had radio operators on ships, and it was pretty well.
Oh, sorry, not radio, radar. That's what I meant.
They didn't have radar. Okay. Radar is still very far in the future from where we are in this story. I'm just telling.
Okay.
So in the 1920s,
you're talking. I get it. Like all these develop, like the electromagnetic spectrum is obviously utilized for communications, radio at this point, and it's very extensively used during war and commercial reasons.
Yes.
But the radar, which is the main topic here, has not been utilized at all. It's not even there.
No.
Okay.
I'm just talking about the very first experiments recognizing that radio waves would reflect from metal objects.
Right.
So in the 1920s and 1930s, people started getting really interested in radio wave reflection experiments, and many countries around the world were exploring this concept. In Britain, especially in 1935, a personality known as Robert Watson Watt. He had a hyphenated name. I don't know why some people have hyphenated names, but anyway, his name was Watson-Watt. Mm-hmm. I had a professor in graduate school, and he started out. I think his name was Bland, Bland. Okay, he started out Bland, and then we broke for the summer, and we came back, and his name had changed to Hawthorne Bland. You could probably look him up. He was one of the professors there. And then everybody went around some prankster went around the department putting Hawthorne in front of everyone's last name on their door. So I was Hawthorne Kramer, and then they had the Xerox machine, so Hawthorne Xerox. It was a joke, but I digress badly.
I was like, okay, where's this going? We're gonna bring this back, right?
Yeah.
Without any prompting on my part.
Right. And anyway, Robert Watson Watt demonstrated aircraft detection via reflected radio waves. And the way I heard that was a pretty cool experiment too. Like he had some officials from the government. I don't remember if I read that they were from the Air Force or what, but they were able to demonstrate like a plane flying over, and it would cause some wavering. They were able to detect it from flying over, and so that so they were actually able to feed the reflected signal into an amplifier because we had vacuum tubes. Once you got vacuum tubes, you can do pretty much everything, because you can amplify. So, and
I don't know anyone still using vacuum tubes, but I'm guessing you're saying that was a revolution.
Today we have transistors and that kind of thing. So it's the same kind of thing, but the idea that the vacuum tube just gave you the ability to do what a diode does, what a little electronic diode does, and it really rapidly developed into a science. I mean, people were, because there were so many great practical applications for radio, and everything else having to do with electricity and electronics, so that was a big deal. He demonstrated aircraft. So Watson Watt demonstrated aircraft detection by reflected radio waves, and this led to the construction of this thing called, we're going to talk about, chain, like a metal chain, like a chain with links, chain home, and that was the secret name. Yeah.
So, by the way, this is a guy that you've been talking about for the last 2 minutes.
Yeah.
He looks like somebody who could have, invented radar.
Yeah, he looks like a nerd. Yeah, he does look like a British nerd. He does look an English nerd. You notice
he's absolutely.
Yeah, they don't like to smile because they have bad teeth. I don't know why they have bad teeth. But
no. I mean, he looks like he's about to smile, but doesn't want to open his mouth.
He doesn't want to show his teeth. Yeah,
is that what it is? Okay.
And if anybody's getting mad at me, I'm just kidding.
Don't. Hey, if anybody's ever upset at Leonard for some offhand remark he says, realize that he's is kidding.
Boomer. Yeah.
Okay. All right. Okay. So, Sir Robert. See, that's the thing, right? He is absolutely British. I mean, his name is like Sir.
He was knighted.
Well, knighted. Sir Robert Alexander Watson Watt. Yeah.
That's right.
So, he went ahead and invented something.
They knew something was up in Europe because there was the Germans. As we've said before, they were in the 30s. The Germans were doing like German things, and
1930s. You mean like gearing up for war?
Yeah. Okay. And they knew that there was that something was up. So and by 1939, really just before the war broke out, during that time, the British built under I guess directed by Watson Watt. They built these what they call the chain home system, and that was the code word for it. That was the code name. The British picked just some kind of weird kind of off. Thing. Yeah, that's it. Okay, and
it looks like a bunch of random radio towers.
Radio towers line the British coast all the way along eventually all the way along the southern coast and all the way along the eastern coast of Britain. And they're these towering steel frames and they transmitted long wave pulses, and they demonstrated that they could bounce off aircraft. They had a range of 120 miles approximately, and they were crude. It's really a crude technology because all they were doing was they were just sending out a signal, right? And then the operators, they used, I guess they used like an oscilloscope kind of arrangement, and so they had operators that were all the way up and down the east coast and along the southern coast of Britain, and they would just train themselves to be able to detect
explain the difference between these 3 and these 4, if you know.
Oh, I don't think there's. I think they're just part of the chain. It could be that they are staggered so that they could.
Wait. Okay, actually, I just read the captions. These 3 are transmitter towers, and these 4 are receiver towers.
There you go. I mean, I didn't really know that. I didn't know the details about the technical details of all that.
This was in Poling, Sussex. Okay, so that Sir Robert guy helped develop this chain home. Yeah.
Mm-hmm. And they tested it and they kept it absolutely secret. And the Germans didn't know what they were doing. This is 1939. The war broke out in the fall.
Let me not go there. Yeah.
Yeah, in the fall.
Sorry, go on.
the war broke out in the fall of 39 in Poland and Central Europe, and British got involved at that time. The United States was not. Canada and Britain and France and all those other countries, they were all on the side were attacked. Where they were at war with Germany. America wasn't at war with Germany until
Well, the
41, really.
the Pearl Harbor bombing. Yep.
But
Okay, go on.
But when the Germans bombed Pearl Harbor, I know. So
Wait, what? Right. Okay.
it's not over till we say it's over.
Okay, so ignoring that historical inaccuracy, but going back to, so we're talking about, since we're mostly focused on the European theater here, all right. But point is, go on.
So what I wanted to say about the chain home system was it was developed very quickly in 1939. They lined the coast with those towers that you just showed.
They demonstrated
they demonstrated that they could detect they could detect airplanes out to 120 miles. And it was fully integrated with a core of observers. And
it actually worked, right? Like, this is a first time that it
worked. Yeah. Whoa.
This was the first time that radar was actively used, like, not for experiment, but for something actually practical.
I think that's accurate. Now, the Germans and many other countries were working on it too, but what I want to say, they had a Royal Observer Corps. That was what they were called, and they had kind of gotten trained to be able to interpret the signal coming back on the oscilloscope, and they were stationed all up and down the coast, and they just used the regular telephone system. Like, if they saw something, they'd pick up the phone and they would call the headquarters in I don't know exactly where the headquarters was, and tell them, I've got a signal coming in. It looks like they're 100 miles out. They're coming, they're coming in, at a certain bearing, and so that's what they had shown that they could do, and they had it up and running, and it was really the first true early warning system for So now Britain wasn't at war with Germany at this time. Okay. Now, here's the neat thing. This is the thing called the Graf Zeppelin II incident. The Graf Zeppelin was an airship. It was the successor to Graf Zeppelin I, which had been retired. Sometimes
that would make sense.
Yeah, and it was referred to as LZ-130. By 1939, airships were pretty much obsolete. People didn't want to use airships anymore.
They still look pretty cool.
Yeah, they do look pretty cool.
Look at that. Look how small the humans are. Well, in comparison.
They look like ants.
Yeah. All right, go on. This is a Graf Zeppelin. This is a Graf Zeppelin too, actually.
Yeah.
This picture.
My mother grew up in the 1930s, and when she was little girl in the 1930s, and she told a story about the Graf Zeppelin. I guess it was the Graf Zeppelin I, the first one, flying along the East Coast, and everybody ran out in the yard and children, come quick, come look at so it was a big deal. So
wait, in the 1930s, your mother saw the Graf Zeppelin?
When she was a little girl, or at least that's a story she told.
And this was it was just like landing in her.
No, it was flying high overhead.
Oh, it was flying high overhead. Okay.
Yeah, it was a
that makes sense.
Luxury travel. It would fly from New York City all the way down to South America.
So this vehicle, however, during World War II, well, I guess we're getting to that.
So, yeah, we're getting to that. So, but by 1939, by the beginning of World War II, the Zeppelins really weren't used for transportation anymore because the Hindenburg and just it just turned out to be impractical compared to other kinds of compared to fixed wing aircraft. And so, but the Graf Zeppelin II was still available to the German Air forces, the Luftwaffe. Luftwaffe means like
I always thought that's a funny name, but that
yeah,
was the name for the German Air
Air
Force,
Force.
right?
You know,
Luftwaffe.
it literally means
Luftwaffe.
like air arm or air armor or air weapon. You know, Waffe. You know,
Waffe. Okay.
Waffe means
All right,
like
all right, all right, all right. So this Graf Zeppelin 2, which was previously used as like a commercial passenger sort of vehicle, is now drafted into the war.
that's right. That's right.
Okay.
And so it was deployed by Germany on this bizarre, I think, kind of bizarre spy mission to probe the British radar capabilities because the Germans were able to see those.
I mean, those
Chain,
towers
yeah,
are pretty obvious.
right. They were able to
I mean,
see
you
it,
can't
and they
miss
didn't
it.
know what it was. And the British were so good about keeping a secret that it was never let out. Right, even though they had
So, so,
like
okay, so back in those days, if you see those kinds of towers, what do you assume? They're just radio communication towers, I guess, because
um yeah, it was yeah, because I don't know what it's a mystery about what the Germans thought it was, but ultimately this mission that I'm going to talk about that was in I think August or September of 1939 failed. And the reason, so they were flying along the coast, and they used the crew. The crew used some radio receiving equipment. It was to look for the emissions, and they failed to recognize what this chain home system was. And so you question, well, why did it fail? What was going on is the Germans had their own radar initiative going on, and they were expecting their system and the two systems that they had developed were using higher frequencies, and they thought they needed higher frequencies because you needed more energy, higher frequencies, higher energy, and also more precision. And the Germans, there's kind of a cultural thing about German engineering and science.
I mean, the Germans were pivotal for
Right.
engineering and science.
So they prized like theoretical rigor and mathematical elegance and perfection in design.
Oh, okay.
And this is the philosophical and academic traditions that come from Platonic forms and systematic purity. So you can think about the philosophers of Kant, Hegel, and so forth. So what that happened is, what I think is, it manifested in like this desire to create technologically elegant solutions, even if they were too costly. And so some people talk about the tanks, in the Second World War. The
Right.
tanks. They were like masterpieces of armored warfare.
Like you're saying, like they over designed it in the seeking
They
perfection.
over-designed it.
Okay.
So
Right.
prone to breakdowns. And so similarly, the Germans had a jet fighter, and we even did a show on
Von Braun.
Brown, about
We did 2 or 3 episodes on Von Braun.
yeah,
By the way.
that the rockets that they were developing were really not that effective. They were effective in terms of demonstrating German technology, but without nuclear weapons, the rockets are really not that important. They're not really that valuable in a war. And I guess maybe we're seeing something like that in current events these days, but I don't want to do that. No. So
let's stick with the past for now.
Yeah, let's stick with the past.
All right, so Germans, they're just flying their little airships. Okay,
right.
So we're getting to that story.
They're flying airship, and the airship was a really good platform for doing this intelligence operation, because they could spend like several days, going up and down the coast of Britain, and they didn't have to explain themselves to the British because they weren't at war, and and actually, I guess we kind of gave the impression that the Germans were flying this over British territory, but I don't think that was the case. I think they were flying off the coast. What I'm trying to say is, the Germans expected something very elegant for radar. They expected high frequency and steerable antennas like we see today, so they but the chain home system was at 25 hertz. So the operators on the airship, on the Zeppelin, they heard this buzz. It was only like that, or and so all that was doing was it was just passively sending out a signal, and then the British had receivers to receive it, and they had integrated them in such a way that they were able to tell how long it took for the reflected signal to come back. And the Germans just did not have the imagination to understand that this was a radar system. So it's kind of a cautionary tale, because it's an intelligence failure. The Germans could receive the signals. They were able to interpret it. I mean, but they just made the wrong choice. In fact, after the war, I heard this story, and I wasn't able to track down the reference for it, but I believe it's true. Some of the radar engineers from Germany and Britain got together to have a conference about it. And in one case, one of the British engineers asked the Germans, "Why didn't you detect our radar?" And the German engineer was astonished at the beginning, saying, "Well, you didn't have any radar." They didn't even know that they had radar.
Okay, go on. Yeah.
I also think that there was some political stuff going on. The Germans had a general named Goering, Hermann Goering.
Okay, yeah. During World War II, yeah.
Yeah, he was kind of a bad guy. And they were, for some reason, emotionally attached to the German high frequency radar system, and they didn't think the British were sophisticated or intelligent enough to be able to do it right. And so they were very wrong.
So they were, in other words, very prideful and thought this technology could only be implemented in the way they envisioned it.
Yeah, I think prideful is the right word for that.
Right.
I think so.
Yeah.
So the Graf Zeppelin was just a civilian airship, and the cover story was that they were doing weather studies about the weather and communications. But the idea was that it could fly legally and innocently in peacetime without alarming the British. So now the Germans did have some evidence, like rumors and that the British might be developing radar, but I think they really thought that the British were very far behind. So
yeah, no, that makes a lot of sense. Yeah.
So
go on. Mm-hmm.
Oh, the basic thing is that the chain home system used a long wave radar, and the Germans were expecting higher frequency, so they just dismissed it. They didn't understand what those towers were. They failed to correlate that the fixed structure layout and that pulsed emission just means buzzing, bzzz, like that. With aircraft detection, they underestimated the British capability. Germany assumed that Britain lagged behind technologically in this area, but actually, so it's actually pretty ironic.
It's ironic in the sense that they're actually ahead of the Germans here.
Yeah, they really were ahead of the Germans in a lot of ways, and
yeah.
And
that's
then,
pretty wild.
I don't remember. 1940 was when the famous Battle of Britain broke out.
Mm-hmm.
Probably a lot of our audience probably doesn't even know any of this stuff, about history. But so
history is interesting.
I can't tell you. I think July through September of 1940, about a little more than a year later, from the time we were talking about the Graf Zeppelin incident, the Britain and Germany were at war, and the Luftwaffe, the German Air Force, attacked Britain, and they did not target those chain home transmitters
because they had no idea what those were.
They thought they were not. They thought they were. They had more valuable targets to hit, like airfields and so forth. So they were concentrating on them. But in all that time, the radar allowed the Royal Air Force
that is so ironic.
Yeah,
Like one of the most pivotal war assets that the
that's
British
right.
had was never targeted because the Germans didn't know what they were.
That's right. Now, I
So
don't want to say none of them were ever targeted, but I think some
right,
of them
right.
were. But the main focus was on trying to knock out the British airfields, and they just didn't have the imagination to think that the British had this available to them, and and actually, like it's like, well, not only the fighters, the because the British also had very excellent airplanes. Their fighter planes were excellent,
Hmm.
and the pilots were well motivated because they're fighting for their homeland and so forth.
Yeah, they're fighting for the homeland
But
instead of trying to conquer somebody else's land.
yeah,
Right.
but these guys in the radar field, there was just a very few of those, and even in a speech to Parliament, Winston Churchill. I don't know if people have ever heard of Winston Churchill, but he was the Prime Minister of England at the time of.
For anybody who knows, who reads things about World War II, for sure, I hope you would have heard of Winston
Well, I
Churchill.
don't. Yeah, I don't know.
Yeah, that's all
even,
right.
I'm not even from this planet, so I don't know. But
You're right,
so
Leonard.
Winston Churchill, he made a speech almost said Congress, made a speech to Parliament where he was praising, all of these people who worked so hard to defend their country. He said, "Never in the field of human conflict was so much owed by so many to so few." And so
You do a pretty good impersonation for the amount of practice you've done.
so
All right,
so
go on.
the I've been trained well. The few included not just those pilots, but those radar teams, that were feeding the information. So that's who he was talking. That's part of some of the people he was talking about in that speech. So now, radar goes global, and World War II pretty much expanded the horizons on radar. Germany did develop advanced radar systems, and they were called Freya and Wurzburg, and it was like a two-pronged kind of system where the Freya system was at a higher frequency than the Wurzburg. They were both higher in frequency than the British system, so that was one of the things. The Soviet Union, they developed radar, and they've deployed it in the Battle of Moscow but with limited integration. We talked about Japan using radio very
During
early,
1905 in the Russo-Japanese War.
But as far as radar is concerned, a lot of technical things the Japanese kind of lag behind in a lot of ways, and it's sort of hard to understand because they were very advanced, in with their airplanes, and naval forces. But the United States kind of lagged behind also, but they caught up fast with the developments of the MIT Radiation Laboratory, and this became like the radar's industrial revolution. So
Okay, MIT something radio laboratory.
MIT is very important for the development of radar. In 1940, the British physicists brought something called a cavity magnetron to MIT. It enabled what they call microwave radar. So it's much higher frequency, smaller, higher resolution, and you could put them in ships, and they were aircraft compatible. You could even have radar on airplanes.
So previously there was no radar on airplanes.
No. So the MIT Radiation Lab, and it's the technology that gives us the microwave oven. It's
This thing, right?
the micro magnetron. Yeah.
Yeah.
There's millions of them.
There's millions of cavity magnetrons.
Yeah, that's every microwave oven uses
Every microwave oven has one of these little devices. Okay.
Mm-hmm. Or something similar. So it became the largest
Very
MIT.
interesting.
Yeah, MIT Radiation Laboratory became the world's largest radar research and development hub, and they invented airborne radar for night and bad weather bombing. And this is during World War II and in the years after World War II. Ground mapping radar fire control radar for anti-aircraft guns. So there's more than 100 types of radar were developed there by the end of World War II. There's another
MIT
thing.
Radiation Laboratory, which is still around, by the way.
Yes, that's right.
So, I mean, for anybody who's interested, the developments go on. Although they have a nice, so they have a nice webpage delineating things they do. Oh wow, this was all back then. Building 20 on the MIT so Rad Lab from 1943 to 1945. ASG Airborne Fire Control Radar. Gun turret of a B-24. Wow.
Believe it or not, there is even a kind of miniaturized radar that was developed that could be put inside of an artillery shell. And it's called the proximity. Incredible. It's incredible. Wow. I still don't understand how it worked, but it's called the proximity fuse, and it detonated artillery shells when they neared a target. And it really is a kind of radar, and it revolutionized, like for air defense, if aircraft are flying over, you could fire anti-aircraft weapons at the rocket, the V-1 rocket, which was a slower moving rocket used by the Germans against the British, and the kamikaze aircraft in the Pacific, and other places in World War II. The proximity fuse, what it was is that it would detonate the artillery shell when it just came close to a large magnetic object or a large radio wave reflector. American and British scientists developed it jointly and very secretly. I don't think that the Japanese or the Germans ever were able to recover one. I think it also, the use of the proximity fuse was limited to over water for a long time because they didn't want it. They didn't want any duds falling in the.
It's one of these guys, right?
Yeah. So
wow.
George Patton said it won the Battle of the Bulge. I don't have an imitation. I can't do an imitation of George Patton. I've never even really heard a recording of his voice.
You just think that's how he sounds.
Well, no, he's quoted as saying, I think he wrote in a book. He said it won the Battle of the Bulge for us. So
short range Doppler radar.
Yeah.
British test with kind of unrotated projectile for unguided rockets. Interesting. Wow. Okay. Wow. There's a lot of history here and actual implementation.
Yeah. So I hope our audience is enjoying this. I'm telling things that they didn't know before. A lot of things in history.
Yeah. So.
Yeah.
Okay. I don't know how to read this thing.
So
I'm sure the radar's up here somewhere.
I've seen that diagram before.
The Mark 53.
I've seen that diagram. That particular diagram, I've seen it before. But like I said, I think that a part of the way these weapons were used, that for some part of the time they were not permitted to be used over land because they didn't want any duds falling into the enemy hands to see what was going on. They wanted to keep it secret for as long as possible. But I mean, let me underscore exactly what it is, because I think we're a little bit careless in explaining what the proximity fuse is. It's a device that gives off a radio wave and a little sensor inside, and you could put it in the artillery shell, right? So that if you fired the shell up into the air at enemy planes flying over, then it would, if it didn't need to actually impact the enemy plane, it could just get close enough to it, and then it would explode, and then cause the enemy to be unalived, as they say these days. So,
unalived, yes, exactly. Since we cannot use other words, let's stick with unalived.
I've seen that. I'm not exactly sure what the origin of that is. My daughter will explain it to me.
You're questioning why we.
Yeah.
Okay.
My daughter will say something like, "Okay, boomer," So let me explain it to you.
You're hilarious.
There was a D-Day.
I'm not going to explain it to you.
At D-Day, the invasion of France that was depicted in Saving Private Ryan and some other popular movies.
Yep, D-Day.
Radar played a huge role in something called Operation Fortitude. They kind of like created a false place, and actually Patton had something to do with this also. Patton had gotten in trouble because he Patton in Italy had gotten in trouble with Eisenhower because there was newspaper reports said that he slapped a soldier and disciplined them for things that were kind of inappropriate, like for PTSD, what they call PTSD today. And so Patton was misbehaving, and Eisenhower got pissed off at him and sent him.
Operation Fortitude.
Yeah. So he said, "All right, listen, you're going up to Scotland or up in northern England somewhere, and you're going to be a dummy general. Well, you're not a dummy general, but you're going to just make a lot of announcements, be visible, make the Germans think that the invasion is being developed in the northern part of Britain, places that were far away from. So it was a deception." So among the things that they did was they created false signals, false radar,
So this was a attempt to pretend to attack in places that they weren't going to attack. Is that what you're saying?
Yes, but also just because the Germans in 1944 were kind of beyond being able to attack Britain anymore, but they wanted the Germans to think that that's where the invasion. They knew an invasion was coming.
Oh,
So
I see. The Germans knew invasion was coming. They just didn't know when. I mean, where? Sorry.
Yeah. So that was one of the things that they did with some radar installations, and Patton was kind of in charge of that. He was, like I said, he was being disciplined. So also, a lot of the radar stations. This is about radar stations and plotting rooms that because like men would go out and fight, and there weren't so there was a lot of opportunities or use of women. So a lot of those radar stations were operated by women. They were called Women in Radar. WAFs. I don't know what WAF is. Women, Army, Air Force, and REN. Women. I don't know what the REN stands for, but that was something that I learned about. And then
women in radar.
Women in radar. So a lot of the operations. Remember, I told you that there was a lot of operators. Yeah. Because
I mean, the men, I guess, were busy actually fighting like in the front lines or something.
I know these days that you're not supposed to talk this way, but men.
There we go.
Men, men who not just men who identify as men, but I mean men who are like what they used to say were, I don't know what you call it. They used to say men were assigned at birth or something. I don't know what that's all about. But anyway, men have objectively superior upper body strength.
Okay, so in order to not sound like a boomer, you're basically saying biological men.
Biological men, but I don't even know if you're allowed to say that. Okay.
Oh my gosh. All right, I think we understand what you mean here.
Yeah.
Basically,
they used to think that objective facts were important, and we now know that that's not true. It's just based upon your opinion and how you feel. Okay, but in the old days, there was this idea that men were distinct from women, and that men had what they call statistically significant and objectively superior strength and ability to fight in a war. And so that's why men would go and fight. And so the men would go and fight, but the women would stay behind. But they had other things that women could do, and women wanted to help. I mean, I don't think any. And
this was in the middle of World War II, so where there was shortages. I mean, there were labor shortages everywhere, in fighting the war, and so every able human being who could fight in some capacity was doing something.
Yeah.
So these women, the radar women of World War II, what did they do?
Well, we talked about the operators that were up and down the coast of Britain, right?
They
So
were mostly women. That's what you're
I
saying.
don't know if they were mostly women, but I know that they made major contributions to that, and I just want
Right.
to say that.
Yeah, that makes sense. I mean,
At some point, I mean, we're kind of getting close to the end of what I really wanted to talk to, but at some point before we finish, you should ask me what Hedy Lamarr did. Okay?
Ward. Yeah, I believe I know that story, and it's a very interesting story.
So the aftermath of all this is that like radar really transformed warfare, air, sea, eventually space, right? So it revolutionized air traffic control, and like we use it. I mean, everybody with their cell phone can check the weather, right? And so you have the weather radar, and
yeah. So can you say that a little bit? Like weather radar, how does that affect? How is radar used to look at the weather?
Well, the radar you can use certain frequencies of radar to see different things in the atmosphere. So, for example, if you tune it to a certain frequency, you can see where the precipitation is occurring. You can detect other forms of radar can be used to detect the speed, the velocity of the water droplets in rain, and determine whether you have any vorticity forming. Vorticity.
Right. Vorticity is a great word. So really, you're saying it's really anything that is changing the path of the radio waves, and when it bounces back, as long as you can analyze it, you can use it to detect anything.
And with
the weather.
in combination with computer technology and sophisticated software, it's that's a thing. That's a thing that's of great utility to us. So that's really all I wanted to.
So, do you think radar was Britain's greatest scientific contribution to World War II?
I think that it is among the greatest contributions of World
Humanity.
War II. To humanity, I mean, even for peacetime use, not just warfare. But I do think that the capability, the capability of the British in developing radar, also cryptology and cryptographic analysis.
Right. That's we should do I would like to do an episode about that sometime. The cryptology,
and of course, the atomic bomb was also probably important. I guess we would say, but anyway.
Yeah. Well, I mean, I think at least for me, radar is one of those technologies which is so prevalent these days. I have not really thought about just how important it has been and still is. So, whereas if you say something like the atomic bomb or the rocket, people are like, oh yeah, of course, those are people. Like, but radar is something I feel like that's something that's out of people's radar. Pun intended, by the way, so to speak. Like the invention radar is not something which people normally think about. They're just like, I don't know. They just take it for granted. So,
right.
Yeah. Now, like, if it was not invented, do you think this world would be very different?
I'm not an expert on that. I suspect that the Germans could have had a really good shot of conquering Britain, at least temporarily. But
right.
Well,
So
I mean, our world would be different. I mean, air traffic
yeah, I guess
control would be much more difficult. And we, prior to the invention of radar, there was a great deal of interest because aviation, military aviation had a 30-year head start over radar, and so there was a lot of interest in being able to hear or see over the horizon. And you can look on the internet and find references to these acoustic horns that were used, and acoustic reflectors, with the idea that you could collect in a big dish, or or literally giant ears, giant things that would surround your ears, to be able to detect the noise of engines over the, even over.
Wait, what is this technology called?
Acoustic detection.
Okay.
Acoustic aircraft detection.
Okay, and this was predating. This was predating the usage of radar.
Right, in the 20s and 30s, when people realized, oh, airplanes are a thing. Okay.
Oh wow. Okay, I think this is probably what you're talking about, right? I think. Like these guys,
that's
Swedish soldiers operating an acoustic locator in 1940.
Yeah. See, you see, they have those big horns there, and so they're used they arranged it in triangle like that, so they could get some maybe a little bit of altitude information, and a little bit of.
This is for detecting sound.
Correct.
Right?
Yes. Yeah.
Okay.
And there's all kinds of steampunky things that you can find, like big horns, with.
That's so interesting.
Yeah.
Never knew that. Acoustic locators.
I think in Britain to this day, they have some big concrete walls that are parabolic in shape. Mm-hmm. And you can go there and view it. They're like in ruins now, but use a parabolic or circular shaped detector that was proposed. I don't know that they ever actually used it, but before, this was one of the things that put impetus to developing the radar.
Nowadays, right, and these days, let me see, using like this kind of stuff, right, at airports. This thing.
Yeah.
Yeah.
But that's radar.
Huh?
That's radar.
That's a radar antenna. Yeah, that's what I'm saying.
Yeah.
Yeah. Huh. What, I guess, like, in terms of so there's like a multiple reflectors happening, I guess. Like it has to, I don't know. These things get complicated.
Well, what it does is that metal surface is isolated from ground. Okay, so it acts like a mirror. Mm-hmm. And will reflect it back to an antenna at the focus.
Okay. Yeah, I get it. So you can think of it as if it's like it's just that we don't see the waves since they're not optical. But it is like a kind of like a mirror, right?
Right. Well, you can't see optical waves either, but except when they enter your eye, then you can see them.
Right. Yeah. Okay.
Right.
Interesting.
Well, let's be clear about this picture here. Put the picture back.
Let me put it back up.
Yeah.
Go ahead.
Let's be clear about what we're talking about. You see the big flat, like curved surface in the background there? Yeah.
Like this thing?
Yeah. That's a mirror. That's a radio wave mirror. Okay. It has holes in it because you can have a lot of holes in it for air resistance, and that kind of thing, because the radio wave is a longer wavelength than the size, the dimensions of the hole. And it turns out that it's a very effective reflector. And then the detector is right there at the focus there.
Is this it? Right. This is a detector?
Yeah.
Okay, so the radio waves, it actually enters from here. It bounces into the focal point here.
Yeah.
And then this, I guess this thing in the back is just like a structural sort of thing to keep it there. I don't know.
I don't know. I don't know. That's a different reflector.
Right. Go ahead. The main point is that, and these things can like swivel around as well, right? Depending on.
Right.
I guess it's just.
Yeah, because it will detect things along the line of sight between the focal point and the center of the dish, the mirror, right? and so it has maximum gain for a source that's very far away. And it's not only that's not only the detector, that's also the transmitter. So the transmitter is also co-located with the detector, and they're like multiplexed, so that it'll send out a pulse and then it'll listen, right? Pulse, listen, pulse, listen. And so the time differential gives you a range indicator. And then
Yeah, that makes a lot of sense.
there's also ways of interpreting the signal so that there's a frequency shift. Frequency shift will tell you something about the speed of the approaching
So,
airplane.
and this yeah, I mean, this goes into aspects of the science of it, like how does it actually these kinds of measurements. But really, like the gist of it is that you're sending signals, and you're transmitting, and you're receiving it, and you're looking at the difference in the frequency of the signal that's received versus the transmitted in order to, I guess, figure out your velocity, and or like the time it takes for it to bounce back, in which you can
That's
figure
exactly
out how
right.
far the range. So yeah, that makes a lot of sense, I would say. Yeah. So in things which are invisible to radar, how do they do that? Or at least reduced radar signatures? Do they just don't bounce back the signal?
Well, in World War II, this was known, and actually the British developed an airplane. It's called the Havilland Mosquito, and it was made mostly out of plywood.
It's not made out of mosquitoes.
It's not made
I'm
out
kidding. That's a joke. Wait,
Yeah.
Haviland. Oh, it's just called Haviland. Okay, yeah.
of
Okay,
called it the Havilland Mosquito, and
this thing.
yeah, and I believe, unless I'm having recollections from a previous lifetime or another expedition to another planet, that it was made out of plywood mostly. It looks great. It looks awesome. Look at those engines.
Yeah, they look fantastic.
Yeah, and it was very fast. And if you remember when we talked about Niels Bohr, maybe
Yep.
not.
Though no, I recall like
Remember? Okay. Well, Niels Bohr was rescued from Sweden because the Germans were advancing. He had just had a conference with one of the German scientists, famous ones, Heisenberg. He had just had a talk with Heisenberg about, and it was in 44 or 40, I think late 44, and he was able to escape because the British sent that very kind of plane to Sweden to pick him up. He was able to escape, and then he couldn't get he was in a very uncomfortable position somehow coming back, and he didn't get the signal. He didn't get word that he should put his oxygen mask on, and he lost consciousness because they were at 20,000 feet or something. And so that's how he was rescued. Niels Bohr.
Niels Bohr was rescued on one of these planes.
That's right.
And how these planes relate to radar is
They were made out of wood. So the only parts that would reflect radar signal were probably the propellers and the engines. And
wooden wonder. Yeah. That is so interesting. Okay, so
Right,
they had
so
a very
that's-
small radar signature. That's what you're saying.
Right. So your question was, how do they do that? Well, the United States especially, but other countries, I'm sure, have developed means of either shaping the signal that's returned by avoiding flat surfaces or vertical surfaces, or by putting radar absorbing, making them out of radar non-absorbing, making the planes out of dielectric materials, and probably a lot of things that are not even revealed, that we don't even know about. But if somebody put me in charge of figuring out how to defeat radar, that's what I would do. I would start making models and putting them in the testing them in the wind tunnel, making little models, and then shining radars at them on a test stand and checking see if I could shape the return signal. and that's how all that works. So today, the United States especially has highly advanced radar defeating technologies that are, like I said, I think they're in the news recently. So, but
Right.
and
Okay.
yeah,
I mean, yeah. I mean, thanks for that informative answer.
well, you're welcome. Thanks for listening.
All right.
That's
All
I
right,
had to-
Leonard.
Yeah.
That's all you had to say. Yes.
Right.
Your alien technology on how to avoid being detected is not going to be revealed to us. See, that's where I was trying to get at.
Oh, no, I'm not
you
going to
know.
reveal our technology.
Yeah, you're not. Yeah.
Yes.
Yeah.
Because that
All right.
gets right into how the mind works. And psychology.
So, now let me. Okay, just two last questions. So, World War II. Do you think the British saw it as a scientific tool or as a desperate defensive last measure?
I don't think they thought it was desperate. I think they thought that it was gave them a tremendous advantage. You know.
Okay.
So certainly
they-
it was important to defeating the Germans in World War II.
Okay. And lastly, do you
I want
think
to say,
radar?
before I leave that subject, the British, to put it, in a earthy manner, the British kicked ass in the Battle of Britain.
You
Okay?
can say that. The British
Right.
kicked
So-
ass. All right.
Let's say that. All right. So
Okay.
okay,
The British kicked ass
yeah.
in World War II, especially against the German Air Force.
And it was, and I don't know what was wrong with the Germans. They weren't. I think some of the German engineers probably knew something was up because they would fly down from the north, and then the British Air Force was right there to intercept them, and then they'd try from the south, and the British were there again. So
It's like, yeah, like how do they know where we are, right? That's probably what the Germans thought, but they
Right.
never did figure it out. Now, could radar have been invented in the 19th century?
Well, that's an interesting question.
Yeah, I posed that to you.
So
So Maxwell, what was it, like mid-1800s, right? Already came up with all that.
no, I don't think
Oh,
so.
was it?
I think really the enabling thing was not only the ability to produce a radio signal, but also
That too.
to produce, but also detect it effectively. Holtzmeier's thing was his radar had a very crude, very. It's almost unbelievable that the detector would even work at all. That was we really to enable radar. We needed amplification, vacuum tubes, and the ability to develop amplifiers, radio frequency amplifiers.
So we needed radio amplifiers, which required the development of vacuum tubes.
Of vacuum tubes, yeah. I mean, in the 19th century, by about 1880 or so, we had electricity. That had come online, but I don't think that we didn't. And there were ways to create radio waves and coherent radio waves. But before 1870, I don't think that would be feasible. I think the top scientists in like 1870, 1860 would understand the concepts. I mean, they would have known they would have understand the physics and the ideas about that, but they wouldn't have any good ideas about how to amplify. We really needed vacuum tubes.
The vacuum tube wasn't developed to amplify radio signals, right?
Oh no, that was what it was for. Yeah.
It was?
In the early about 1910 or so, 1911.
Okay.
In the United States, mostly. I want to say also at MIT, but I'm not sure. The vacuum tubes. Somebody observed that if you have a grid and you apply a electric voltage to it, that it would repel
Yeah, this is for people who haven't seen vacuum tubes, which are most of the younger population, I would assume. This is kind of what they look like.
yeah. These were gigantic. Like some of these were
They're
15, 20
huge.
feet long. Yeah.
Right, so these things were like, and like the name suggests, they're tubes with, like, these are just vacuum inside, right?
Yeah. A look like a regular radio that you would use would be the size of a house.
Yeah. Wow. That's ridiculous. So
Yes,
these things
right.
you're
That's
saying were
ridiculous.
specifically created, or not create? Yeah, they were specifically invented to help amplify radio
Well,
signals.
well, people were playing with this with the vacuum technology as you know. We talked about the Crookes tube. Remember the
Yeah, that was
Crook
so
and
cool.
Thompson? You know, he was putting like metal. Well, the cathode ray tube was invented, and the cathode ray tube emitted electrons, and the electrons would go across. So they would try to put grids in front to see what would happen when I put like a grid. Right there we go, in front of the filament. So we have a current flowing from the cathode to the anode in this case, and then there's a grid in front. You can I guess you can see
Okay,
it in the middle.
the
in the
grid
middle.
is just
Right.
like what, a metal wire?
Yeah, that's a metal wire. And so
Okay.
this is derivative from the technology that J.J. Thomson and using the Crookes tube. I'm working from memory right now. So Thomson had a vacuum tube, a long vacuum tube, almost like a television tube, although it wasn't television. I mean, but he had a cathode and an anode, and then he played around with electric fields and magnetic fields and putting things, and then he would take like a little Playboy bunny caricature and silhouette and made out of metal and put it in the middle, or a dinosaur, or something called a Maltese cross, which I think is really lame. But he put that in there, and then he could see that it would block the flow, right? And he could see that image on the screen. So it was only so then he put something in between the anode and the cathode that you could put a charge on it. You could actually change the electric charge. And the physics of this is really interesting. Actually,
and that's what the grid is, right? The thing in between, is that what you're saying?
Yeah. So if you put a voltage onto that, then it greatly changes the current flowing from the anode to the cathode. And
interesting.
That's the story of the vacuum tube.
Okay, and I guess doing this, I suppose how does it amplify the signal? Or is that really difficult
No.
to explain?
No, it's not difficult to explain at all. Okay, the principle is that grid is not attached to is not electrically connected to either of the anode or the cathode. The anode, I guess in this one they have a filament and plate. Okay, the filament is the cathode, the plate is the anode. If there's no grid there, then if you apply a voltage to the filament, and then you heat that filament up, electrons are flying out of it, and then they will flow to the other side. They'll flow to the plate. So you have a current flowing, right? So there's a current flowing.
The current is flowing from the filament. The electrons are flying from the filament to the plate.
Yeah.
Okay.
And so in the 1910s, that period of time, people were playing around with this. And they said, I'm going to put, because J.J. Thomson, put barriers in there, and he could see the electrons were blocked by it. That's how they knew that there were electrons. Okay, so anyway, there's a current flowing between there. So now let's put a filament. Let's put a grid between there.
Put a grid in between it. Yeah.
So, so you notice something happening with the current that's flowing. You can measure the current. If you put a grid in there,
okay,
it will moderate the current. Okay, if you apply a tiny little voltage to the grid relative to the filament, it makes tremendous differences in the amount of current that's flowing from the filament to the plate.
Apply a tiny voltage to the grid, which is that little wire in the middle.
Yeah,
and it'll affect it affects the electron flow rate, in other words, the current, from the filament to the plate.
That's right. And so that's what we call amplification. That's how an amplifier works.
Because you could, instead of having a little bit of a current flowing from filament to plate here, you could have a lot.
Well, you can take a small signal that's coming into the voltage that you apply to the plate. I mean, to the grid. A little,
Okay.
like let's see.
Oh,
A return signal from
Right.
a reflected.
I get it. The voltage okay, so the tiny voltage is going through this thing in the middle, the grid. So
Yeah.
okay, so the detector, or whatever, the signal is causing a slight voltage difference in the grid.
On the grid, okay. Yes. And then that changes the amount of current flowing from the filament to the plate by a tremendous amount. So that's what we call amplification.
Right. Okay. Excellent. Yeah. All right. So without actually doing any math, Leonard here just explained it conceptually, which is great. So it seems like we could, if you want to, you could make a vacuum tube, right?
Yeah, you could make a vacuum tube. You need to learn about
fairly simply.
You need to learn how to blow glass. And you need to learn how to achieve very high vacuum.
Okay.
Because it doesn't work in air. The air just ionizes and just turns this whole thing to crap.
Right. I hear you. Okay, so must occur in vacuum, of course.
Yeah.
All right. So next science project, if
you need a vacuum, you need to learn about vacuum technology and also making glassware.
Yeah, I see. That should be interesting if I get there.
Yeah.
All right. So, hey, good that we threw some science in here in terms of a visual explanation of what this does.
Yeah. By the way, I also made a joke a little while ago. I said that the vacuum tubes were like 15, 20 feet long. That's not true. Most of them are about that big, about 2 inches.
The joke is that they're large, but they're not.
They're always talking.
large.
Everybody in the comment says, "Oh, vacuum tubes are very large."
Actually, you know what? This is actually this is a good example. This is like a little. These are the vacuum tubes.
Yeah.
And so,
well,
if
you can't really see anything for scale, but you could hold the vacuum tube in your hand right there.
Well, these are like little wire ports. It looks like 1943.
Yeah. You can still buy them. They're made by companies in Russia. They might be embargoed, but people.
What would you do with vacuum tubes these days?
Some people like to use them. Well, first of all, there might be very old equipment that still uses them, but as far as the technology is completely overtaken by semiconductor transistors and semiconductors. But some people might want to. You might want to do it for fun. Some people say that you get better, audio or audio high fidelity from using amplifiers.
If you buy like a high fidelity audio amplifier, do they have vacuum tubes?
I would doubt that there are any that exist today.
Okay.
I do remember when I was little, radios, desktop radios that you would put on the back of your chair, on your desk, or televisions. If you look down there were tubes, and you had to go to the store and buy the tube. Like every electronic store, sometimes a drugstore would have a tube tester. Okay, and it was like for retail use, and you could use it for free. You didn't have to pay for it, but it was the stores that sold the vacuum tubes, and they were everywhere. I mean, because vacuum tubes were going out all the time, so you could take all the tubes out of your set. You could take them to the store. I seem to think it was the hardware store or even the drugstore had these tube testers, and I have done this. Okay, so I have living memory of doing this. So you take the tubes and you put them in there, and there was there was like a manual, and it was straightforward because the tubes were fairly the style of tubes are very common. So you'd put them in there, and then it would give you a test reading, where the needle would go all the way over into the green zone, or it would be over in the red, and then you have to buy a new tube. So you go buy them, and they were like $1 or two, something like that. And then you go back home and you put them back in your television. Televisions especially were notorious for having tubes that would go out, but also radios.
Right.
Yeah.
So you could easily replace all the parts in your radio or TV back then.
Well, the problem with the tubes is that because they have a heated filament, their lifetime was limited. They would go out just like a light bulb will go out. They'll burn out eventually.
Okay.
So it was a maintenance activity,
Right. Okay, so they were. Yeah, I see what you mean. It was known that they're gonna fail because they're gonna burn out.
So that's
right.
yeah. And I think you can go on Google right now and you can dial in a name, a particular kind of vacuum tube, and you will find vendors that are selling vacuum tubes.
That's great. Who knows? I mean,
yeah,
the wonders you can do. That's still there.
Yep.
Yes. Okay, so do we have anything else to say?
Okay.
I'm not. That wasn't entirely a tangent. Like vacuum tubes, to go into full detail, probably need an episode of its own at some point.
That would.
But
yeah, we can do that. Yeah.
Yeah.
Yeah. You were going to ask.
Thanks for stopping by.
Yeah. You were going to ask me what Hedy Lamarr did.
Oh yes. Tell me. What did Hedy Lamarr do?
Was a well-established movie actress in the 1930s.
Yeah.
Okay.
I found it. Well, I find it astounding that she was, like what you said. People know her for the movies, but she's also a very famous inventor, I suppose.
And so, yeah, she's an inventor, and people talk about her. A lot of like people who also like worship Tesla. Nikola Tesla, like he did some great thing. Not that he didn't do a great thing, but it wasn't that great. We could do the biography of Nikola Tesla. So anyway, but besides being an actress who had the attention of the movie industry and so forth, somehow she got acquainted with another engineer. And
George Antel.
Yeah, and so she's credited with inventing frequency shifting technology.
Right.
It wasn't ever really. It was proposed, or it was suggested to the Navy the U.S. Navy in World War II, and the idea is that you could defeat jamming of radio or acoustic signatures from submarines and so forth for submarine control by rapidly changing the frequency that you're transmitting on in some coded manner, and this is a technology that's used for
the frequency hopping spread spectrum.
Right. So if I have a transmitter and its frequency, like it has a different frequency, I can change my frequency from one to another. Like I can go from frequency A to frequency B to frequency C and so forth. Right. And I could do that in a synchronized manner. Then my receiver can be listening at A, B, C at the same time. And that way I can put a code on top of my transmission. And therefore, that gives me the ability to keep from being intercepted, either interfered with.
Very interesting,
right?
Yeah.
So this actually is used for GPS, in particular, GPS, and also for Wi-Fi technology. They were not able to exploit it during World War II. I want to say also that although she gets a lot of credit for this, it's
shit. I mean,
I don't know whether I want to say it or not. It's sort of an obvious kind of thing. I mean, it's not.
What do you mean? That she's very pretty?
I mean
what?
That besides that, okay.
Well, I mean, like, I mean, I think she gets credit because isn't it true that she and this other guy, George A. Hill, was the first ones
Yeah,
to develop
and
this?
so and she was sort of she
Yeah.
was kind of dork nerdy. I think she
Yeah.
was nerdy,
She
and
absolutely,
self taught.
with her father, who would take her on walks to explain how devices function. I
Yeah,
think I read a quote somewhere where she wished she was known more for her like inventions than like just acting. But
yeah. I don't know. I think I heard that too. But I find that hard to believe because what actors do is they become known for things. That's what actors do. You get in front of people and you create a character. So I mean, but
interesting.
anyway,
Yeah.
that's a kind of a almost apocryphal story.
Well,
Um,
2014, Lamar was posted and inducted in the National Inventors Hall of Fame for frequency hopping spread spectrum technology. Okay, so
I
clearly
think it's
she's
fine.
recognized for it.
I think it's
I
fine.
mean, I think if you came up with something, you should be recognized for it. Like
Yeah, and
that's
I'm
only
all
right.
about that. The whole history of our podcast. I've always tried to mention the contributions of women to physics and so forth. So
Absolutely.
I think that
So,
is
oh, cool. Also, like a quantum telescope on the roof of University of Vienna is named after her in 2014. I guess she's originally Austrian, right? Yeah, that makes sense. So, yeah, cool. Um, oh, this must have been the patent. By the way, all these inventions you could still find them in the U.S. patent right system.
of
Like you could
course.
just
Yeah,
yeah.
of course.
So everything we talked about basically,
Yeah.
I think. So
Mhm.
yep. So you can read original notes by the inventors for more details, technical details. So. Leonard, I guess you just gotta invent something, and then we can name a unit after you.
Yeah.
Or so it would be interesting. I don't know what the Kramer would mean. Like, what is one Kramer or two
Um,
Kramers?
I don't know. I don't
Gosh,
think I could say really. Yeah.
Okay, you can't say it without getting in trouble. I get it. So, all right. Okay. All right, everybody. Before I close this out, I do have to say thank you for all our wonderful supporters and listeners. I've been keeping the ticker on the bottom, but just to give a shout out to Kyle Baker and John Graves, who has contributed monetarily every single month on the Patreon site. So patreon.com/c/sgd on space. So if you want to do that as well, or you just want to be a follower, you could go there. And of course, on YouTube, you should like, subscribe, and share, as I always say. And please feel free to leave
It's
comments.
really important. I like to see comments, but
Like Joe, thank you for saying nice show. I appreciate you watching. Next time, feel free to ask a question. So, and I know there's a number of you all out there who's watching but hasn't posted anything, which is fine. But I encourage you to do so if you have any questions. We do look back at this, so indeed. All right, we will be back next week, right? Talking about another exciting topic.
yeah, we'll think of something.
Indeed. So,
So
all right. With that, we shall
Be
call it a
well.
day. Be well.
Good afternoon, good night, good morning.
Wherever you may be. And to our viewers from 10,000 years in the future, you guys already know everything. So this is just for your entertainment. So
Tell me how the stock market did this week. Send me a signal.
send a message back in time, indeed.
All
So
right, bye.
bye.
Good night. Namaste.